Show me your vote. Come on, show me. Okay, be honest. If you have this displayed, you get 3 points.
Which one? Let me see.
At x equal a, f is definitely not continuous because remember, okay, flashcard, look. Okay, I say the keys of this class a lot, but that's because you have to remember them. One key to this class is precision. It's not knowing something kinda, it's like knowing it precisely. So a function is continuous at a point if this is true. The limit from the left, the limit from the right, and the value in the middle are all infinitesimally close to each other. So when you look at this picture, at x equal a, the limit from the left is like this point. The limit from the right is this y coordinate. The value of the function at a is this y coordinate. Those are definitely not all close to each other. Jacob, please.
Can you also say it's continuous if you don't think of your pencil?
Yes. It's a good way to do a graphical problem for sure. I brought up the flashcard just because there'll be written questions where you have to know that.
Okay.
For this one, the idea that I can't draw this without picking up my pencil is good enough. So definitely not continuous at A, please.
So it's not continuous at A, but you can still find the limit of just A, not A minus and A plus, because the two sides are the same, correct?
Yes. I want everyone to vote. When you're trying to find the limit, as x approaches A from the left, right, and then as x approaches A from the left, so you're trying to answer D. When you look at this graph, raise your hand if you can tell me where should you be looking? Like what should be grabbing your attention to answer this? This is a really good example of doing the work won't help. You've got to be thinking the right way. If you're not thinking the right way, you'll miss it every time. So what should you be looking at, Mario?
I would be looking at just the line where it's approaching A from both sides.
So I'm going to draw some dots. I want you to tell me. I'm going to just draw a few dots. I want you to tell me which ones you're looking at. So we've got the open circle here. We've got the closed circle here. 2 points for Mario. I've got this green dot here. You can't really draw these dots. We just pretend that we can. And I've got a purple dot here. So raise your hand. What color should I be looking at to answer D? Which of those 4 colors should I be looking at to answer D? Let's go, Morgan.
What's the green and then wait,
You're okay.
yeah, the green and then the one on the, I don't know.
Kind of hard to tell. Are you looking here?
Yes.
You're awesome. Don't worry. It's hard to tell that color. So Morgan is saying green and purple. Who agrees? 2 points. Yeah, your eyes should not be looking at the red because the red is located at x equal a, which has nothing to do with what's happening when x is just getting close to a. Question? Please.
Wait, but at x equals a, like if like a dot existed where the hole is, like that's where, like that's the value of the limit, right?
Kinda. I know what you're asking. It's a good question. If there's a dot here, still not true actually. When we find the limit, we never get to x equal a.
Okay.
The idea is you're trying to get infinitesimally close to x equal a without ever being x equal a. So even if there's a dot there, you should still not be looking at that dot. Even though in a practical sense, if this were, say, 5, yes, we would say the value of this limit is 5.
Okay.
Is that your question?
So like technically the value of the limit is like 4.9 repeating forever, but we write it as 5.
No, the word limit means what value are you getting infinitesimally close to being, not what value are you. Do you hear the difference? So the value that we're really at is 4.99999 forever. But what value is that infinitesimally close to becoming? 5, so the value of the limit's 5. Does that answer your question?
So like, isn't like the whole where like the value of the limit is? Like,
Yeah, that's why I said when I said you're kind of right.
okay.
That the value of the limit is 5, but it doesn't really help to solve limit problems to look here. That tends to mislead people. Like they'll look here and they'll mess it up. Like you don't want to look there, you want to look infinitesimally close to there.
Okay.
Even though it does become the value of the limit. Good?
Yeah.
Please.
Will they ever give you a problem where A is more than 1 point?
Like something like this? Is that what you meant?
No, like it'd be like wider but still disconnected, kind of like a.
Oh,
piecewise
like
function.
something like this, where there's a big gap.
Yeah.
Is that what you meant?
Yeah.
I've never seen them do that. There you go. Okay, so this one's false.
So that's our answer. But
Oh, that was exciting.
how is that a relative maximum?
Points for the whole room. Raise your hand if you can tell me what little piece of Danica's chart I should draw to remind me where f has a relative maximum. What's the little piece of Danica's chart? I always do this. But I always draw when I'm trying to remember what would cause f to have a relative maximum. What do I always draw? Connor?
When clock goes from
Or you're okay.
goes from
Like I need both columns.
it goes from increasing to decreasing,
Good work.
and then prime when it goes from positive.
Good. So this is what causes f to have a relative mass, not f prime.
Okay.
So because I'm looking at f, I don't look at this. I just look to see if f is changing from increase to decrease. And if I pretend that I can follow the dots, I get to this dot, the next dot is up or down? Up. The dot after that is up or down? Would you call that an increase to a decrease?
Yes.
Yes.
All right, that makes sense.
Good question. Do I have more questions on this one? It's actually smart to keep going. It says x is equal a is in the domain of f. Domain means is the x coordinate of a an x coordinate where there is a y coordinate. Yep, so that's true. We already found out that these are equal. If these are equal, then this is the same. Question?